Hello everyone. This video is on the Knewton Alta assignment for section 6.6 part 1 called Solve Logarithmic Equations. Alright, so in this video I'm going to be doing a preview version of this assignment. So please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are all the same, the structure should be similar, so I'm hoping that watching me do these here helps you in some way when you're working on the assignment on your own. Now on your assignment page, you should be seeing the title, the mastery bar telling you how far along you've gotten, your objectives. Looks like there are 3 objectives for this assignment. Pardon me. Beneath the current objective, there should be a question related to that objective. And at the bottom of every question should be a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button. It's for instructors only. But you will have a more instruction button. If you're struggling with a topic or a question, click on this. You'll be taken to a page with some reading or videos to study, and then you'll be given questions related to that instruction. And completing those questions is another way to progress through the assignment. Alright, so the first objective I'm looking at is use the definition of a logarithm to solve logarithmic equations. Alright, so I'm going to write out this equation here. Now it's just like any other equation. Right? When you're asked to solve an equation for a variable, you're trying to find values that you can replace that variable with and make a true statement. And when they say, use the definition of a logarithm, that basically just means, hey, do you remember how to change back and forth between logarithmic form and exponential form? Right, you may recall this, that if the logarithm, base b of, say, m, if that was equal to some number n, right, this is in logarithmic form, remember this was equivalent to saying the following, that b to the nth power was equal to m, right, that capital M. Right, and this is exponential form. And this should look familiar from earlier in chapter 6, going back and forth between these. So this is going to be key for this objective anyway, where they're asking us to use the definition of a logarithm to solve equations. So this first example, this first question I'm given is, you have the log base 2. The argument of that log, the input of that log, is the expression negative 6 times x plus 46. And when is this equal to 4? Right, we're asked to solve this. Find a value for x that would make this true. Well, the variable I'm trying to solve for is inside a logarithm. I want to eventually rewrite this so that the variable is not inside a logarithm anymore. So that's where I have a logarithm equal to a number, just like in my logarithmic form up top here. In order to be able to get at that variable, I need to change to exponential form. Alright, so here I'm going to change to, I'll just put exp form, right, exponential form. So this would be equivalent to saying that negative 6x plus 46 must be equal to 2 to the 4th power. Right, that's the equivalent exponential form. And then we solve this equation for x, and of course check our solution back in the equation, the original equation. So this is, negative 6x plus 46 equals 16, right? 2 to the 4th power is 16. Then subtracting 46, negative 6x equals negative 30. And then dividing by negative 6, x equals positive 5. And then, of course, as with all equations, right, you should be checking your solutions either with a calculator or by hand. If I were to replace x equal with 5, negative 6 times 5 is negative 30, plus 46 would be 16, and we'd get the statement the log base 2 of 16 equals 4, which is totally true, right? Because 2 to the 4th power is 16. Remember, logarithms are exponents. The log base 2 of 16 is just, the exponent 4, right, that I would need to raise the base 2 to get 16. So this works. Right, so the solution to this equation is 5. And that's what I'm going to enter back in the assignment. And after you submit an answer, you'll be told if you're right or wrong, and then you'll be given some sort of answer explanation. Please read through the answer explanations just to make sure you understand why something was correct or incorrect, and hopefully you can learn from your mistakes for future questions. All right, next. Okay, so now we're asked to use the one-to-one property of logarithms to solve logarithmic equations. So I'll write out what that property is. Right? Now, logarithmic functions are one-to-one functions. Right, remember, for like f of x equals the log base b of x. If you look at a logarithmic function, I'll just quickly refresh your memory as to how the graphs of these look. Now remember, there were two cases. One, if the base was bigger than 1, the graph looked like this. And the vertical asymptote at the y-axis, and it was an increasing function, right? And if the base was between 0 and 1, it was a decreasing function. 1, 0, b1, right around the graph. And again, the vertical asymptote at the y-axis here, and it was a decreasing function like that. But still, one-to-one functions, right? And again, this is going back to probably, I think, chapter 3 of this text, or the chapter 3 assignments. Remember, a function is one-to-one. If it passes, these are one-to-one functions. If it passes the horizontal line test, right, you draw any horizontal line, it's only going to hit the graph one time, never more than once. And that meant if you had two different inputs, they'd go to two different outputs. And another way of saying that is if you have two outputs that are the same, two outputs of a logarithm, so say the log base b of m is equal to the log base b of n. So if this is happening, well, because they're one-to-one functions, the only way these two are going to be equal is if their inputs are exactly the same. Because like I said, two different input, the inputs can't be different, because two different inputs would take you to two different outputs. They'd never be equal like this. So if you have two logarithms with the same base equal to each other, then their inputs must be equal. And this is called the one-to-one property for logarithms, that I just put in that box there. All right, this is the one-to-one property that they're talking about in the name of that objective. All right, so the goal here, if we're to use this property to solve a logarithmic equation, the goal is to get a statement like this, where you have a single log on one side equal to a single log on the other. So what we're going to do is condense both sides, write both sides as a single log. And you may recall in section 6.5 what it meant to condense logarithmic expressions, right? Use the properties of logarithms, the quotient rule, product rule, power rule, to try to write both sides as a single logarithm like I have here. And then once you see that, you have an equation where there's a single logarithm on both sides, then you say, oh, must be that the inputs are equal. Right? And then you jump to a different equation without logarithms. So our first example is the following. Our first question, we're asked to solve the following. Find the log. Remember, this is log base 10 if there is no base written, common logarithm. The log of x plus 11 minus the log of x minus 5. When's this equal to the log of 9? And this is just, there's no variables over here. This is just a number. The log of 9 would be something between 0 and 1. Alright, so I can't use the one-to-one property just yet. Again, I'll bring it back up. Remember, if I want to use this one-to-one property, it's got to be a single log equals a single log. Right, we have to condense using the properties of logarithms, again, that you saw in section 6.4, 6.5, I believe. So over here, I have the difference of two logs, log minus log. So I'm going to use that quotient rule for logs, and I'm not going to write it up. I'll just hopefully remember it. This can be written as a single logarithm. This will be equal to the log of, and then the argument of this log is just the quotient, the fraction made up where x plus 11 is the numerator, divided by, and then x minus 5 is the denominator. Equals, and then the right side is already a single logarithm, right? It's just a log of 9. And now I have what I want if I'm to use the one-to-one property, right? The only way two logarithms base 10 are going to be equal to each other is if their inputs are the same, right? Because two different inputs can't give me the same output. So by the one-to-one property, I'll just write 1-to-1. This input on the left, x plus 11 divided by x minus 5 must be equal to the input on the right, which is 9. And now we're solving this equation. So first I'll clear fractions, multiply both sides by x minus 5. Now if I multiply 9 by x minus 5, and distribute the 9, that'll be 9x minus 45. And then I'll take away 9x, it gives me negative 8x on the left. Take away 11, gives me negative 56 on the right. And then dividing by negative 8, x would be positive 7. Now again, don't forget to check this. And you always check in the original equation, the way things were originally given to you. Right? Because you got to remember that, the number inside a logarithm has to be positive for you to get a real number output. So make sure, that when I plug in 7 for x, all the numbers inside the logarithms are positive. All right, 7 plus 11 is 18. 7 minus 5 is 2. So the log, we'd have this. We'd have the log of 18 minus the log of 2 equals the log of 9, and all the numbers inside the logarithms are positive. So this should be good, and then you could use the quotient rule to say, yeah, this must be equal because this would be the log of 18 divided by 2, which is the log of 9, right? That works out. Okay, so and this is our only solution, right? So the solution to this equation is 7. And that's all I'll enter here. X equals 7. Submit. Great. And again, please read through the answer explanations. Alright, so back to this one where we're asked to use the definition of a logarithm. This is again just changing from logarithmic form to exponential form and solving for the variable. Now this time, we have a natural log, a log base e. So we're going to have a calculation involving e. So they're asking us here to round our final answer to 4 decimal places, right? The nearest 10,000th. All right. So first, I'll write this up. All right. So this equation, we have the natural log of negative 5x plus 1. When's this equal to 3? All right, so like with the first equation from this video, first example, right, I'm going to change this to exponential form. Now remember, this is base e. All right, so this, if I change this to the equivalent exponential form, that would be negative 5x plus 1 must be equal to e to the 3rd power, or e cubed, whatever that is. Then I would subtract 1. So negative 5x equals, e cubed minus 1. And then divide both sides by negative 5. So we have x equals, whatever e cubed minus 1 is, divided by negative 5. And this is what I'm going to enter in the calculator and round to 4 decimal places. Right, now the calculator I'm going to use is a free online calculator at desmos.com. And just calculate it off to the side here. We have e to the 3rd power minus 1. Notice I put that in parentheses, because it's all in the numerator, divided by negative 5. And rounding that to 4 decimal places is negative 3.81710, so 8171. So this here, this is what they want. And again, you can check this. Now if you were to plug in the exact form, you'd get 3 equals 3. If you plugged in this rounded version, the left side would be something close to 3 equals 3. It would be an approximation, but it should be good. And I'll leave it to you to check that. So back in the assignment, now they don't, they say don't include x equals, right? Just put in the number, put in the solution, negative 3.8171. Right, I believe that was it. 8171, yes. And submit. Excellent. All right. Next. All right, so now we're into the other objective we haven't seen yet. Use logarithm properties and the definition of the logarithm to solve logarithmic equations. So in these examples, these questions, first you're going to, one of the sides will have a bunch of logarithms. You are just going to use the properties of logarithms, right, as they're saying here, logarithm properties. The product rule, quotient rule, power rule, right? You're going to use the properties of logarithms to get a single logarithm. Condense the side with all the logarithms on it. And then that definition of a logarithm, right? Then take that single log equal to a number and change it to exponential form and solve, and then check your solutions. So if you couldn't follow what I was saying there, hopefully you'll follow these equations that I'm writing. All right, so the first equation we're given here under this objective, we have the logarithm, base 2 of x minus 1 plus the logarithm base 2 of x plus 5 equals 4. So, I can't just change to exponential form right now. This side is not a single logarithm equal to a number. It's the sum of two logs. But I can, use that product property to make this into a single logarithm, right? Condense it. Log plus log, equals a single log, right? So the log base 2 of, and then the input of this log is just the product of those two inputs, right? So the quantity x minus 1 times x plus 5, which I will multiply in a second, right? And this should be equal to 4. And now I have what I want. I have a single log equal to a number. And then just like in previous equations, now that I have this single log equal to a number, I can change it to exponential form, and then we'll get an equation that we can solve for the variable. Now, in exponential form, the input here, x minus 1 times x plus 5 would be x squared plus 4x minus 5. Right? If you FOIL, do x minus 1 times x plus 5, you get x squared plus 4x minus 5. And this should be equal to 2 to the 4th power. Or, 16. Should be equal to 16. And now I have a quadratic equation. Right? And you should know by now how to solve quadratic equations. Good step for solving quadratic equations, good first step is to take everything to one side. So we have x squared plus 4x, and then if I were to subtract 16, this will give me minus 21 on the left side and equals 0 on the right after subtracting 16 from both sides. And now I could use the quadratic formula if I wish, or this is solvable by you can factor this pretty easily. This factors to x plus 7 times x minus 3, and then I have this product equal to 0. And remember, a product is only equal to 0 when one of the factors is 0. Right, so this leads me to the following equations. So either x plus 7, the first factor, is 0, or x minus 3, right, the second factor, is 0. And then solving each of these, get x equals negative 7 or x equals positive 3. Now, like I said before, you're going to want to check these, especially back in the original equation, because these are logarithms, and the number inside a logarithm, when you're done simplifying, shouldn't be negative. So how about x equals negative 7? Right? If I plug in negative 7 for x, we'll have the log base 2 of negative 8, which is already a problem, plus the log base 2 of negative 2, negative 7 plus 5. Is this equal to 4? As I said, this is an issue. Right? You have negative 8 inside that logarithm. You have negative 2 inside that logarithm. The input of a log must be positive in our studies. Right? Must be positive. So negative 7 is not good. We're not going to use it. That's what one of those extraneous solutions. Now how about x equals 3? If I plug in 3 for x, we have the log base 2 of 3 minus 1 is 2, plus the log base 2 of 3 plus 5 is 8. And is this equal to 4? Yeah, you have a positive number in this log, a positive number in that log. You could use the product rule and make this the log base 2 of 16, 2 times 8, and the log base 2 of 16 is indeed equal to 4, right? 2 to the 4th power is 16. So this works out. This is our only solution. The other one's extraneous. So after all that, the only solution is 3. And they did say if there's more than one answer, separate them by commas, but there's not more than one valid answer. Only 3 works here. And you'll see them explain that here. Wonderful. So another equation like that, very similar to the last example. So let me just write this out and we'll work it out. So we're given the log base 2 again. It's not always going to be base 2, right? But of x plus 2 plus the log base 2 of x minus 5 equals 3. Alright, so once again I'm going to use a property of logarithms. Because I see the sum of two logarithms over here, we can condense this, write this as a single log using that product rule. This is going to be the log base 2 of, and then x plus 2 times x minus 5. Right. The log of a product equals 3. Now I have a single logarithm equal to a number. So I can very easily change this to exponential form. I'm just going to put exp right now for exponential form. Now x plus 2 times x minus 5, when you multiply those, that would be x squared minus 3x minus 10. Right. Equals, and then 2 to the third power is 8. Right. So I'm just going to write 8 on the other side, but that's 2 to the third power. And then subtracting 8 from both sides, I now have x squared minus 3x minus 18 equals 0. And this is factorable. This actually factors to x minus 6 times x plus 3. And this will only be equal to 0 if x equals 6 or negative 3, right, when x plus 3 equals 0. But now let's check them again back in the original. And you're just trying to make sure that when you plug these numbers in and simplify the number inside a logarithm, that the number inside the logarithm is still positive. When x equals 6, 6 plus 2 is positive 8, so that's okay. 6 minus 5 is positive 1, which is okay to have inside a logarithm. So 6 should work if I know I did everything correctly. Negative 3 on the other hand, though, negative 3 plus 2 is negative 1. You can't have negative 1 inside a logarithm, right? Only positive. So negative 3 is extraneous. Our only solution is 6. Right. Now, because these last two examples had an extraneous solution, doesn't mean it's always going to happen. You may come across questions where there are two solutions. Right, just make sure you're checking them. Okay, good. All right, so back to the one-to-one property, where again I'm doing more properties of logarithms to get a single log on one side equals a single log on the other side, and then I equate their inputs and solve that equation. All right, so once again I'll write out the equation we're given. So on the left side I have the difference of two logs. It's log base 10 of x minus 6 minus the log base 10 of x minus 7 equals the log of 2. Now the right side is already a single log. It's the left side. And we saw a question like this earlier. I had the difference of two logs. So I can make that a single logarithm with a fraction inside, right? The numerator would be x minus 6. The denominator would be x minus 7. Equals, log of 2. And then by that one-to-one property, the only way two logarithms with the same base are equal is if their inputs are equal. So x minus 6 divided by x minus 7 must be the same value as 2. And then again I can clear fractions pretty quickly, multiply both sides by x minus 7. So the left side will be x minus 6, and then 2 times x minus 7 would be 2x minus 14 right after distributing the 2. Then if I subtract x, I'll have x on the right, and adding 14, I'll have 8 on the left. X equals 8. And don't forget to check it. 8 minus 6 is positive. 8 minus 7 is positive. Remember, as long as you have positive numbers inside your logarithms after you plug in the values and simplify, you should be good. So 8 is our solution. Great. All right, next. All right, so using this one-to-one property again. Now this one's nice. They have logarithm equals logarithm, and it's already a single log on both sides, right? And then we're asked to round our answer to the nearest tenth. Right, round your answer to the nearest tenth. So we're going to be probably using a calculator here and rounding. All right, so once again, the equation we're given. We have on the left side the log, again base 10 of, and then inside that log is the expression 6 times the quantity x plus 3 equals, and then another log on the other side, a single log, and then inside that is just 7 times 8x. I don't know why they wrote it that way. That's just 56x. So yeah, I can use the one-to-one property right now. The only way these two are going to be equal is if their inputs are equal. So if 6 times x plus 3, which I'm going to distribute the 6, that's 6x plus 18 equals, and then the input over here is 7 times 8x, which is just 56x. And then subtracting 56 gives me 18 on the left. Subtracting 6x gives me 18 on the left, 50x on the right, and then I divide by 50. X equals 18 50ths, which if you multiply by 2 is 36 hundredths, but another way to write that is 0.36. Right, you could have also used a calculator. Now they didn't want this, right? They want us to round this to the nearest tenth, which is only one decimal place. So 0.36, that would round to 0.4. That's why I got the approximately here. And this is what they want us to enter. All right. And of course you can check the 0.36, they'd be equal. If you check 0.4, they'd be close to being equal. They'd be approximately equal. Yeah, so and then they said put a leading 0 if there's a number between 0 and 1. Right? So 0.4 is our rounded answer. Great. All right. And looks like one more of these one-to-one properties, and it's another one where both sides, they already have a single log. So I can use the one-to-one property immediately and just set the inputs equal to each other and solve for x. And once again, we're asked to round the answer to the nearest tenth. Right? Just remember to read the instructions. Make sure you know how they want you to enter your answers. Right, so back to the paper. So on the left side, I have a log of 5 times the quantity x plus 6 equals the log of 8 times 9x. Alright, so again, I can use the one-to-one property right away. Right? It's already a single log equals a single log. So the inputs must be equal. Right? So 5x plus 30, right, that's what I would get when I distribute the 5 here, must be equal. Now 8 times 9 is 72, that's 72x. Okay. Subtract 5x, we have 30 equals 67x, and then divide by 67, x is 30 67ths. And then I'll punch this in. Now this one's not as easy to get to be over 100 like I had before, or over 10. So let's punch that in the calculator. So 30 divided by 67. And if we're rounding this to the nearest tenth, it's 0.44, so 0.4, right? That would stay 0.4. And that's what I'll enter, 0.4. Great. Alright, so it looks like that objective involving the one-to-one property is done. It's got the two other ones to finish, and we've seen examples, of the two other ones. Alright, so here's another one where I'm just using the definition of a logarithm, right? Just changing to the equivalent exponential form and then solving. And round to 4 decimal places again this time. So I have the natural log, right? That was log base e of negative 3x plus 5 equals 6. I change to the equivalent, exponential form, and again, you can only do that when you have a single log equal to a number, like this. So negative 3x plus 5 must be equal to e to the 6th power. And that would subtract 5 and divide by negative 3. So we have x equals e to the 6th minus 5 in the numerator, divided by negative 3 in the denominator, and I'm going to punch that in the calculator round to 4 decimal places. Alright, so back on the calculator. E to the 6th minus 5 in the numerator, divided by negative 3 in the denominator. So yeah, the solution is approximately negative 132.8096, right, if you're rounding to the 4 decimal places, the nearest 10,000th. So negative 132.8096. That's what I'll enter here. Negative 132.8096. Great. Alright, moving on. Alright, so looks like one more of these. Again with a base e, round to 4 decimal places. Alright, so I'm just going to kind of talk this one out loud. You'd have 4x minus 2 equals e to the 5th power. And then you would add 2 and then divide by 4. So it'd be e to the 5th plus 2, all divided by 4. Alright, so here, and just going back to the calculator, e to the 5th plus 2, all divided by 4, and then rounding to 4 decimal places. 37.6033. Right, it's 2/8, so round to 3. 37.6033. And there we go. That should be good. Great. Alright, now I got one more objective to complete. And we're using properties of logarithms to condense a side, condense an expression to a single logarithm, and then changing to exponential form. So once again, I'll write this equation out. So we have the log, again, base 2. Please understand that it doesn't have to always be base 2. Of x plus 7 plus the log base 2 of x plus 1 equals 4. This side becomes the log base 2 of the product of x plus 7 and x plus 1. Because you got the sum of logs becomes a product, log of a product, equals 4, and then I change to exponential form. Now the product of x plus 7 and x plus 1 would be x squared plus 8x plus 7 equals, and then 2 to the 4th power would be 16. And then I'll subtract 16 from both sides, Got x squared plus 8x, and then 7 minus 16 be negative 9. And then this factors to x plus 9 times x minus 1. And the only solutions to this equation are either negative 9 or positive 1, or both. I mean, these both could work, but you got to check them out. Now I'm hoping it's obvious that negative 9 won't work, because if I plug in negative 9 for x, negative 9 plus 7 is negative 2. You can't have a negative number as your input of a logarithm in this text, right? In our studies here. So negative 9 is extraneous. The only solution will be 1. If you plug in 1 for x, you'll have 8 and positive 2 here, and that would end up being the log base 2 of 16 equals 4. That works out. So the only solution to this equation is 1. Alright, and then I should just have one more from this objective. Okay. So this one I'll just talk out loud. We have the log base 2 of x minus 5 plus the log base 2 of x plus 2 equals 3. You'd put these together as the log base 2 of x squared minus 3x minus 10. And then you change to exponential form, get x squared minus 3x minus 10 equals 8. And then it becomes x squared minus 3x minus 18 equals 0. X minus 6 times x plus 3 equals 0. X equals 6 or negative 3. 6 works. Negative 3 would be a bad choice for x because you have negative numbers inside. So the only solution to this one is 6. And again, with some practice, you might be able to get that quick at these. But write it out if you wish. It doesn't matter. All right. Great. Again, please read through the answer explanations. And that should be it for this preview version of this assignment. Like I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, structure should be similar. So I'm hoping that watching me do these examples here helps you in some way when you are working on the assignment on your own. And thank you very much for watching.